All right, hi everybody, welcome back. We'll pretend this is Friday morning, so we're going to start off right where we left off on Wednesday afternoon. We were working this problem about heating up a mixture of ethane and propane. So I'm just going to go right back to where we left off in class and continue solving this problem. Okay, so if you remember right, we had used that STP flow rate to figure out that we had 89.3 moles per minute coming in and 89.3 moles per minute going out. We had the mole fraction of methane, the mole fraction of air. That's the same on both sides. Remember where chapter 4 stuff is done, where it's steady state in an open system, we're assuming that moles in equals moles out because there's no chemical reaction. So that's the only way it could be if we're at steady state. So then that leaves us with the energy balance. And we showed in class today the energy balance reduces to delta H equals Q. So now I'm going to continue with that. I'm going to do it a slightly different way than what we did in class for the example today. I'm going to show you that instead of doing the CP for a mixture, you can do the delta H for both components and then add them together. That's one thing we had talked about in class on Wednesday. So I can say delta H here is equal to the sum of the outputs minus the inputs. All right, so what we're saying there is we're going to take the molar flow rate of all the species leaving and their enthalpy, and then subtract off the molar intake of all the species entering in their enthalpy, and that'll give us the total enthalpy change for the process. All right, now to do this, we have to calculate what all these molar values in and out are, and what all the enthalpy values in and out are. So what we're going to do is we're going to build something I call an enthalpy table. If we can fill this table up with all the information we need, then we can use that to plug into this equation, solve for the rate of enthalpy change, and then ultimately solve the energy balance for Q, which is what the problem's asking us to solve for. So I'm going to build my enthalpy table. Let's see, I'm going to come over here so we don't have to erase it for a while. And then I'll do my substance. I'll do the moles in, and the enthalpy in, the moles out, and the enthalpy out. All right, I've got two substances here. I've got methane, and I've got air. All right, so what I need to do is I need to figure out how many moles of methane I have coming in, how many moles I have leaving, and what's the enthalpy of each, and the same thing for air. If I can fill this table out completely, then I have all the information I need to plug into this equation right here, so I can solve for delta H and ultimately solve for Q. Now to get the moles of methane and air in, it's pretty easy. Like you guys remember from chapter 4, you're just going to multiply the mole fraction by the total number of moles. So for methane, that's 8.93 moles in, and for air, 80.4. All right, same thing here, 8.93 moles in, moles out, and 80.4 moles out. All right, so this is looking pretty good so far. On this table, I basically need 8 values, and I've already got 4 of them filled in. So now I need some enthalpy values. Now, anytime you build an enthalpy table like this, you have to choose a reference state. Do you remember what a reference state is? Anyone? A reference state is a state that you arbitrarily choose, and at that state, you say enthalpy values are equal to 0. Remember, we can't really measure enthalpy directly. We only measure changes in enthalpy, just like potential energy. You don't measure potential energy directly, you just figure out changes in potential energy. So for enthalpy, we have to figure out one point where we're going to arbitrarily say enthalpy 0, and then we're going to base all of our other enthalpy values off the change from that arbitrary reference point. In chapter 7, you guys used the steam table. Everything in the steam table has the same reference point, which is the triple point of water. But here, we're not going to use the triple point of water. We're going to pick a reference state that makes it easier for us to do our calculations. All right, so I'm going to pick 2 different reference states here. So I have to pick a reference state for every compound I use. but I get to pick it, okay? There's not many things in your life that you have complete control over. Think about it. You have to answer to your parents, you have to answer to your professors, but this is one thing that you have control over. You get to pick the reference state when you're doing an enthalpy problem. So for the reference states I picked here, for methane, I picked gas at 20 degrees Celsius and 1 atmosphere. So I have to pick a phase, solid, liquid, or gas. I have to pick a temperature, and I have to pick a pressure. So I picked methane, gas, 20 degrees Celsius, and 1 atmosphere. For air, I picked 25 degrees Celsius, 1 atmosphere, and of course that's also a gas. Now, if I were you, I'd probably be thinking, this makes no sense. Why did he pick two different reference states? Are you thinking that? Well, it's a good question. I'm going to explain why. We pick reference states that make our calculations as easy as possible. If I pick methane as a gas at 20 degrees Celsius and 1 atmosphere as my reference state, that means that anytime methane is a gas at 20 degrees Celsius and 1 atmosphere, the enthalpy value is 0. Now it's not really 0, okay, but we're just arbitrarily saying it's 0 because that's our reference point. And we're going to do all of our calculations based on the difference between where we are and the value at our reference point. So if you think about it, our methane coming in is at 20 degrees Celsius and 1 atmosphere, and it's a gas. So that means our enthalpy in for methane is what? Anyone? Sounds like you said 0. Okay, that's right. It's not really 0, there is some enthalpy, but because that's our reference state, we say at our reference state it's 0. So by picking this as the reference state for enthalpy, I can make one of these values 0, and that makes my calculations easier to do. Now, is the enthalpy out for methane going to be 0? It's not, because it's not at the reference state coming out, right? It's coming out at a different temperature. It's coming out at, what do we say? I forgot the temperature coming out already. Oh yeah, it's coming out at 400 degrees Celsius. Hold on. I've got a Righto here. Now that's funny. The problem I showed you guys on the screen is not actually the one we're solving. All right, sorry about that. Let me put the screen down real quick to remind you what problem we're solving. All right, my apologies. This is actually the problem we're solving, right? 10% methane and the balanced air heated from 20 to 300. Sorry about that. This is the problem we're starting with. All right, now let's get back to it. Okay, so because this is at 20 degrees Celsius and 1 atmosphere, that's 400 degrees Celsius and 1 atmosphere. So here, the enthalpy value is 0 because that's our reference state. It's not going to be 0 here because it's not at our reference state anymore. So that's some unknown enthalpy value. I'll call this value H1. Now, you may be thinking for air, how come you didn't pick 20 degrees Celsius as well to make that value 0? And the truth is, I could have done that, but I picked a different reference state. I picked 25 degrees Celsius and 1 atmosphere as a gas. Anybody know why I picked that for my reference state instead of picking 20 like I did for methane? It's because I want to be able to use table B8 and B9. If you want to be able to compare enthalpy values in tables, you have to use the same reference state that they use in that table. So in B8, the reference state is 25 degrees Celsius and 1 atmosphere as a gas. So I'm going to use B8. Right now, these are unknowns. So I'm just going to call them H2 and H3. But instead of having to use B2 and do an integration for a mixture for air of nitrogen and oxygen, I can just use table B8, which will make this a lot easier. All right, so let's think about what we've done. Let's not lose sight of the big picture here. We're trying to get these enthalpy values compared to their reference state. Remember, enthalpy is a state function, so it doesn't matter the path you took. You're just trying to compare the values to a reference state. You're going to plug them into this equation right here. So now I know all the n values. I just need to know the h values and I can solve. Well, there's 4 h values, right? But one of them is 0. So now I need to do h1, h2, and h3. Once I have those, I'll have everything I need to be able to finish this problem up. All right, so how do we do those? First, let's do h1. What does h1 represent? That represents the enthalpy difference between methane at 400 degrees Celsius in 1 atmosphere and methane at 20 degrees Celsius in 1 atmosphere. So you could think about it as you could say H1 is basically the difference between the enthalpy value of methane at 400 degrees Celsius in 1 atmosphere and methane at 20 degrees Celsius in 1 atmosphere. So that's our reference state. We're comparing our true value to our reference state. So to get this delta H, final minus initial, I can just integrate. So I integrate from 20 degrees Celsius to 400 degrees Celsius using the Cp for methane gas dt. Where am I going to get the heat capacity for methane gas as a function of temperature? Anybody remember? It's from table B2, that's right. So I'm going to go to B2 in the back of the book, that table in Appendix B, and I can get this Cp for methane. So I look up the Cp for methane, and I integrate, and I can get that enthalpy value. So that's H1. Okay, and I'm not going to write in the whole Cp and do all the integration for you. You should be able to do that. But that comes out to be 12.09 kilojoules per mole. All right, again, let's think about the physical significance of this. This means for methane, its enthalpy at 400 degrees Celsius is 12.09 kilojoules bigger than its enthalpy is at 20 degrees Celsius. All right, so this is 12.09 kilojoules per mole. Again, I made that look easy on the board, but in reality, to get that value, I had to look up that nasty polynomial, plug it in here, integrate it, evaluate the integral with respect to 420, and then solve it, do a lot of complex math to get this. That's why for air, I picked this reference state, so I can just use B8 to get H2 and H3. So now I'm going to get those two from B8. So let me erase this. And I'm going to go to B8 for air. And I get H2 is equal to negative 0.15 kilojoules per mole. All right, I had to use that with B8, and I had to interpolate. All right, I know what you're thinking right now. Hey, that doesn't make any sense. Why is that enthalpy value negative? Why is it negative 0.15? Can anybody tell me why it's negative? Anyone? No. All right, think about what our reference state is. Our reference is methane at 20 degrees Celsius. Or sorry, air at 25 degrees Celsius. I'm sorry, we're talking about air. The reference state is air at 25 degrees Celsius. H2 represents air at 20 degrees Celsius. So if you compare the enthalpy of air at 20 degrees Celsius to the enthalpy of air at 25 degrees Celsius, it's going to be lower. Because it's 0 at our reference state, this is a little bit lower than 0. It's a negative 0.15. So H2, negative 0.15 kilojoules per mole. H3, I don't even have to interpolate H3 because the value for 400 is in the table. H3, 8.17 kilojoules per mole. All right, so that's super convenient. That is way, 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 way the heck easier than integrating, right? I can just look that value up right there in the table, plug it in, 8.17 kilojoules per mole. So that's the value and the beauty of using B8. All right, so I interpolate here, no interpolation, but now I'm done. So if you look at my enthalpy table, everything in the enthalpy table is filled out. So all I need to do now is plug it into this equation up here. So I'm going to erase right up here. And I'm going to say Q is equal to delta H. And then I'm just going to plug in. So everything coming out. So I've got 8.93 moles of methane times 12.09 kilojoules per mole. Right, actually for methane it's a rate, so it's a mole per minute. All right, so that's this number times this number. Now I have to do this number times this number to get the enthalpy in the exit stream of the air. All right, so that's 80.4 moles per minute times 8.17 kilojoules per mole. So that's the output, that's this portion. Now I have to subtract off the sum of the input. So the input, I'll have minus 8.93 moles per minute times 0 from this term right here, minus 80.4 moles per minute times negative 0.15 kilojoules per mole. All right, now I'm looking pretty good because this is just simple arithmetic. You've been able to do this since probably, I don't know, some of you 3rd grade, some of you 11th grade, but somewhere around there you've been able to do that since then, right? So now you just solve and you get Q equals, let me see if I can read my writing here, 776 kilojoules per minute. That's kilojoules per minute. They asked us for the answer in kilowatts, so I have to do a little bit of unit conversion here. I'll say 1 minute, 60 seconds, and then I'll say 1 kilowatt is 1 kilojoule per second. If I solve that, I get Q 12.9 kilowatts. That's an ugly looking K. 12.9 kilowatts. All right, a couple of points I want to make on here. Does your answer seem to make sense? Is it intuitive? Well, we can at least check and see if the sign makes sense. This Q is positive, and that means I had to add energy, add heat. I guess is the best way to think about it. I had to add heat to raise the temperature. That makes sense. You should have to add heat to raise temperature, right? The other thing I want to point out is I picked those reference dates because they were easy for me. All right, 20 degrees Celsius for methane meant one of my values was 0. 25 degrees for air meant I could use B8. What if you pick different reference dates for me? Could you pick a different reference date than the ones I picked? What do you think? Yeah, you could have. You could have picked 20 degrees Celsius for air. You could have picked 500 degrees Celsius for methane. You can pick any reference date you want. And as long as you do all the calculations right, you'll get the exact same answer. So don't feel like you have to use, oh, I have to use the exact same reference date as him. I just pick the ones that make the calculations most convenient. But you can pick any one you want. All right, so that's in general how you solve a problem where you're doing either a pressure change or a temperature change. That's number 1 and 2 in our 5 types of processes we might have to see. Any questions on this problem? All right, no questions, but it is on YouTube, so you can actually go back and watch it again if there's something you're not clear about. I would definitely encourage you to work this problem on your own, by yourself, compare your answers to my answers, and see if you get the same thing. If not, ask Mr. Pendergast to see if he can help you finish it up. All right, so we're done with this problem now. Let me erase this, and then we'll put the slides back up and move on. All right, so we got a gear change here. We're going to our third type of process. So we did phase or pressure change with constant temperature and phase. We did temperature change with constant pressure and phase. Now we're doing a phase change. If I keep the temperature and the pressure the same, and I change the phase, how does that affect the energy diagram? Or how does that affect the energy balance? And it turns out it's pretty significant. We're going to see that in these calculations, but in general, it takes a lot more energy to have a phase change occur than it does to make something heat it up or cool it down. So if you're working problems that have energy balances and they have a phase change, if you forget to do the phase change, you're in a big mess, all right? So phase changes are really important. All right, if you think back to the steam tables even, the specific internal energy and the specific enthalpy for a liquid, they're much lower than for the vapor at the same temperature and pressure. Why is that? You probably remember that from chapter 7. Okay, you just have to add a lot of energy to help those vapors escape the liquid and become, or help those molecules escape the liquid and become a vapor. But the big difference in those two, that seems to suggest that there's a big change in internal energy and enthalpy associated with a phase change. And that's what we see. If you look back at the steam tables, if you remember right, you can see the enthalpy for the liquid, and then a couple columns over, you see the enthalpy for the vapor. The vapor is always much bigger. So that seems to imply vapor enthalpies are much bigger than liquid enthalpies, which is true, which means you have a big change in enthalpy and internal energy when you have a phase change. Okay, this means we have a lot of heat transfer that's required for a phase change to occur. And we're going to have to calculate that in our energy balance. And again, for energy balance for a closed system, for us, it's typically going to be Q is equal to delta U. Q is equal to delta H for an open system. So how is this delta U and delta H affected when we have a phase change? And that's what we're going to look at in this portion of the chapter. All right, you guys remember the term sensible heat that we talked about on Monday? Today we're going to talk about latent heat. That's the other kind of heat I was telling you about. Latent heat is heat that you don't really see the effects as far as temperature. I can add heat, but the temperature doesn't go up. And if you think about it, you guys probably learned in high school, if you're boiling water, right? The water, you add a lot of heat, the temperature of the water will go up until you get to 212 degrees Fahrenheit. Then the water starts to boil. If you keep adding heat, what happens to the temperature of the water? It doesn't change, right? Why doesn't it change? Because all that energy is being used to evaporate the water. Once all of that water is steam, if you keep adding energy, keep adding heat, what's going to happen to the temperature of the steam? It's going to go up, right? But initially, the boiling water's at 212 and the steam's at 212. There's no temperature change even though you're adding heat. That's what latent heat is. So latent heat, you can think about it as the enthalpy change associated with the transition of a substance from one phase to another at a constant temperature. So I'm adding heat, it's just not sensible heat because the temperature is not changing, right? So that's called latent heat. There's a couple different terminologies that you should get used to that you'll see in your book. One is the heat of vaporization. Okay, that's the enthalpy change associated with going from a liquid to a vapor. Delta H, final minus initial. The initial is the liquid, the final is the vapor. The difference between those two is the heat of vaporization. There's also the heat of fusion or the heat of melting. That's the specific enthalpy difference between solid and liquid forms at a given temperature and pressure. Okay, these values are often tabulated, but remember they vary greatly with temperature, not as much with pressure. They're pretty much independent of pressure. At least for this class, it's okay to assume they're independent of pressure. If I want to know a heat of vaporization or a heat of fusion or a heat of melting, I can get that information in B1 in the back of my book. Remember, B1 is the one that's alphabetized with all the different compounds in there. If you're interested in a particular compound, like, I don't know, chloroform, right? You can go to chloroform in the back of the book. You can look up the heat of vaporization and the heat of fusion, heat of melting. Again, remember, when Mr. Pendergast is giving you guys a problem on a test, he's not going to say, hey, don't forget for this problem you need to know the heat of vaporization, which can be found in B1. He's just going to assume that you realize you need to know the heat of vaporization and that you need to look that up in B1 and you know where to find that information. So make sure you check that out in B1 and realize what's back there. We're going to do a couple of examples though to show you how to use that information. All right, here's one. At what rate in kilowatts must heat be transferred to a liquid stream of methanol at its normal boiling point to generate 1,500 grams per minute of a saturated methanol vapor? All right, again, let's think about physically what's going on. I've got 1,500 grams of methanol, liquid, and I want to add enough heat to convert it to a vapor. I'm not going to change the temperature. I'm just simply boiling the methanol. How much heat does it change, or does it need? All right, let's work on that one together. By together, I mean I'll do it all by myself, and you'll watch. All right, so I go to B1. All right, that's methanol. If you haven't had organic chemistry yet, that's how people typically write in shorthand. All right, methanol. So I can go to B1, and I can get the heat of vaporization. All right, that's how it looks in B1. It's got the delta H, it's got the little V for vaporization, and it's got the hat on top letting us know this is a specific property, right? It's kilojoules per mole in this situation. Okay, 35.3 kilojoules per mole. I can also get the boiling point because it tells me it's at the normal boiling point. I also get that from B1. The normal boiling point means the boiling point at 1 atmosphere. All right, so this is just an energy balance problem at this point, right? We got Q is equal to delta H. There's no kinetic energy change, no potential energy change, no work, no moving parts. We're just adding heat. So Q is equal to delta H. So in this situation, that's equal to N times delta H hat. And our delta H hat is just the heat of vaporization, because the only enthalpy change we have is the enthalpy change associated with the vaporization. Remember, there's no sensible heat here. There's no temperature going up, temperature going down. The only reason we have an enthalpy change is because of a phase change. That's process 3 in the 5 types of processes I told you guys about on Monday. So phase change at a constant temperature and constant pressure. That's what we're doing now. So the only enthalpy change we have is due to the vaporization. So here, I just say Q. I don't know the molar flow rate, but I know the mass, so I can just convert that. So there's 32 grams of methanol in 1 mole of methanol. Okay, and then in 1 minute, there's 60 seconds, right? So that's the molar flow rate of methanol. That's going to give us units of moles of methanol per minute. So that's this. And then I'll multiply that by the heat of vaporization. So the heat of vaporization, 35.3 kilojoules per mole. And then I'll throw in a kilowatt because they asked me in kilowatt, 1 kilojoule per second. Okay, so that's pretty simple math. When I plug that in and solve it, I get Q is equal to 27.6 kilowatts. What does that represent? What's the physical meaning of that 27.6 kilowatts? Is it positive or negative? It's positive, right? What does that imply? That implies heat had to be added to the system from the surroundings. Does that make sense? If I have liquid methanol, I want to convert it to a vapor, I'm going to have to add heat. So that makes sense, right? So this is the amount of heat I would have to add, 27.6 kilowatts, to boil 1,500 grams per minute of methanol that was already at 64.7 degrees Celsius, right? No temperature change. So the methanol liquid is 64.7. After the vapor forms, what temperature is the vapor at? 64.7, you got it. All right, so a simple example there to show you how that works. Now let's move on to one that may not be quite as straightforward. All right, here we go. All right, one thing that made that example so easy was the fact that the heat of vaporization was given to us at the normal boiling point, and our actual system was at the normal boiling point. What if we're not at the normal boiling point? How does that affect our calculation? All right, so here's an example where we're not at our normal boiling point. It says calculate the heat of vaporization of water in kilojoules per mole at 50 degrees Celsius and low pressures from the tabulated heat of vaporization in B1 and data in table B2 and B8. So it's asking us to do this problem two different ways. Compare your answer with the answer given in the steam table. Why are they different? Okay, so we're going to do this two ways. In reality, you wouldn't really have to solve a problem like this with steam because you could just look it up in the steam table. But if we wanted to solve it for steam, we could, so we're going to solve it. Now, your question is, hey, the heat of vaporization, can water boil at 50 degrees Celsius? What do you guys think? Can water boil at 50 degrees Celsius? It can if the pressure is low enough, right? Because normally water boils at 100 degrees Celsius, but that's assuming we have 1 atmosphere of pressure. If the pressure was lower, water would boil at a lower temperature. So it's completely reasonable to say that we have a heat of vaporization at 50 degrees Celsius. That's physically possible. That's not irrational in any way. But notice in the problem it says at low pressures, because water's not going to boil at 50 degrees at 1 atmosphere. The pressure would have to be lower than that. But we don't know the exact pressure here. All right, so let's see if we can solve this problem. All right, so I'm going to go to table B1. And for B1, I know the normal boiling point is 100 degrees Celsius. And I know the heat of vaporization is 40.656 kilojoules per mole. Now you may be saying to yourself, that doesn't help us because we're not at 100 degrees Celsius, which is true. But I'm going to show you how we're going to use the fact that enthalpy is a state function to use these data to get what we need. All right, here's what we're really trying to calculate. We're trying to calculate if we have water is a liquid at 50 degrees Celsius, and we take it to a vapor at 50 degrees Celsius, what's that heat of vaporization? All right, that's what we're trying to solve. That's what's happening in real life, okay? In real life, liquid water is going to water vapor at 50 degrees Celsius. We don't know that value, it's not in our book. So how could we solve a problem like this? Think hypothetical. Think imaginary. Think state function, right? Remember when you and me went to the beach together in Miami? That's the same thing that's going on here. We can't solve this problem the way it's written, but we can do an imaginary pathway to take us from the starting point to the same ending point and calculate the enthalpy along the way and use that to get this value. So here's what we're going to do. We're going to do an imaginary pathway. We're going to pretend like we take water to a liquid at 100 degrees Celsius. Then we're going to vaporize it so that we'll have vapor at 100 degrees Celsius. And then we're going to heat it back up. Again, this is imaginary. This is not what's really happening, but it doesn't matter because enthalpy is a state function. So in our imaginary world, we'll have some enthalpy change here, delta H1. We'll have some enthalpy change here, delta H2, and then we'll have the heat of vaporization at 100. And if I add H1 plus HV plus H2, that's going to give me this value up here. Again, this is the real value, but I can't calculate it. But I can calculate all three of these pretty easily. I add them together, it's going to give me that value. All right, that's the beauty of a state function, that you can use these imaginary pathways. So the truth is, the heat of vaporization at 50 degrees Celsius is going to be equal to delta H1 plus the heat of vaporization at 100 degrees Celsius plus delta H2. If I can get all three of these and add them together, that's going to be the same as this value up here. All right, so now I just solved these three. So delta H1, the problem statement told me to use table B2 and B8 the first time I do it. So I'm going to get H1 with B2. I would never do this, right? I would use the steam tables. But because it told me to use B2, I'm going to use it. So delta H1 equals the integral from the initial temperature, 50 degrees Celsius, to the final temperature of 100 degrees Celsius for the Cp of liquid water dt. I got that from B2. So I looked that up in B2 and I integrate that heat capacity. And let's see, that comes out to be 3.77 kilojoules per mole. Again, I'm not going to do all the math for you. Check that math on your own, but it's 3.77 kilojoules per mole. All right, so I know one of my three pieces. Now my second piece, heat of vaporization at 100, I've looked that up here, 40.656. Bam, I got that. All right, now all I need is H2. H2, I'm going to get from B8, like the problem statement told me. So delta H2 is equal to the final minus the initial. So the final is the enthalpy of vapor at 50 degrees Celsius minus the enthalpy, specific enthalpy I should say, of the vapor at 100 degrees Celsius. So I get this from B8 and interpolate, and that comes out to be 0.84 kilojoules per mole. This one I get from B8, I don't even have to interpolate for that one. It's 2.54 kilojoules per mole. So the difference between those two, H2, is equal to negative 1.7 kilojoules per mole. Does it make sense that it's negative? You betcha, right? Because you're going from 100 degrees Celsius to 50 degrees Celsius, that enthalpy is going to go down. So here, that's negative 1.7 kilojoules per mole. Okay, so if I add 3.77 plus 40.656 minus 1.7 kilojoules per mole, I do that math, it comes out to say the heat of vaporization at 50 degrees Celsius equals 42.7 kilojoules per mole. That's using B2 and B8, like the problem statement told us to. All right, so what do you notice here? If you compare that to this value, they're not that far off, but they are off, right? There's about a 5% difference in these two. So you have to remember the heat of vaporization is a function of temperature. And if you're not at your normal boiling point, you have to do something like I just did to account for it. All right, so that's using B2 and B8. What did it tell me to do for the other way? Okay, so I use B1, B2, and B8. It says now to do it with the steam tables to compare the difference. All right, so let me erase this and get it with the steam tables. All right, so in the steam tables, I can just look up in the steam tables. B5 is the one I used. It's called evaporation in the table instead of heat of vaporization. I think it's called the heat of evaporation, but it's the same thing, right? And so we say the heat of vaporization at 50 degrees Celsius, that's equal to 2382.9 kilojoules per kilogram. All right, so this is what I get from B5 in the steam tables. All right, so is this the same as this? 42.7 kilojoules per mole, the same as 2382.9 kilojoules per kilogram? I don't know. I can't compare two things that have different units, right? So I've got to do a unit conversion. So I'll say 2382.9 kilojoules per kilogram. And then I'll say 1 kilogram is 1,000 grams. And there's 18.01 grams and 1 mole of water. 42.9 kilojoules per mole. All right, so with the steam tables, that was a freaking heck of a lot easier, right? See how quickly I could do that? And I got 42.9. 42.7 is what I got with the imaginary pathway. They're close, but they're not quite the same. Maybe a couple percentage points difference there. Why are those values different? Or let me ask it a different way. Which one of those values would I trust more? Do I think 42.9 is more correct? Or 42.7 is more correct? What do you think? Sounds like you're all saying 42.9. Why are they different? Okay, it turns out that to get water to boil at 50 degrees Celsius, the pressure would have to be 0.12 atmospheres, right? That's pretty low pressure. In this example, we pretty much solved it just like the pressure was 1 atmosphere, right? Because in our imaginary pathway, we vaporized it at 100 degrees Celsius, which would be at 1 atmosphere. So here we assume the pressure was at 1 atmosphere. In the steam tables, they know the pressure has to be 0.12 atmospheres. So this slight variation you see is from the differences of the pressure. So heat of vaporization is a function of temperature to a great degree. To a lesser degree, it's also a function of pressure. And you can see how it changed with the pressure here, but because this one's at the actual realistic pressure, That's the number that I would trust more right there. Okay? And this is how you want to solve a problem with water anyway. You want to use the steam table. All right, that's all for that problem. Let's move on. We don't want to waste any time. All right, let me erase this. Okay. In this class, not as much, but sometimes in your other classes, like in thermo, there may be times where you need to do a estimation of latent heat. You can't look up the heat of vaporization in the book for some reason, so you have to estimate it. There's a lot of different ways to do that. Any one of these estimations you use is going to introduce some error, and you'll see that more in your Thermo 1 class. But you can check out in your book, they describe a few of those: Trapping's rule, Chaitin's equation, Clausius-Clapeyron equation, the Clapeyron equation, Watson's correlation. All these take into account the species, and they give you a way to estimate the latent heat. They're not as good as the methods we just used, but they're quicker and give you a good estimate. All right, I think it's been about 50 minutes, so we're going to stop here. Pendergast will be back on Monday. Hope you guys have a great weekend. Thanks.